So so that's the criterion I have to satisfy for the heat equation to be stable. And it has very dramatic consequences on the error analysis. Because if you look at the equation satisfied by the error, it actually satisfies the same equation as the numerical scheme. So if you look at the error, okay, the error that is defined as how do we define it? I mean, some people define it one way, some people define it the other way. Yeah, we define it as the difference between numerical and analytical solution, Wi minus Wi analytical. Okay, and if you look at how the error evolved from one step to another step, what you get is the following. What you get is that if you apply the discretization to EI, what you get is DEI, not DEI dt. What you get is EIN plus 1 minus EIN divided by delta t is going to be equal to, of course, Wi minus Wi between the two time steps minus Wia analytical minus Wia analytical between these two time steps, right? When you apply the finite difference operator in space, you also get very similar conclusions. It's just equal to a linear subtraction between the same differential operator operated on the numerical solution, which is what I denote as W, and the analytical WA I plus 1 plus WA and I minus 1 minus 2WA. Okay, so basically both sides of the differential equation applied on the error can be written down as a function of the discrete operators operated on numerical solution and on analytical solution respectively. Now, if you look at what is the difference between the two sides of the differential equation operated on the error, what you get is the first term, which is operated on the numerical solution, actually cancels out, right? Because they are the numerical solution is actually what we solve. So the left-hand side is the time derivative, the approximate time derivative actually equals to the approximate spatial derivative for the numerical solution, but not exactly for the analytical solution, right? So on the first column, these two matches, the time derivative, spatial derivative, they cancel out. On the second, do they cancel out? The second column, the difference is analytical solution, right? The unknown exact solution. They actually don't exactly cancel out. And what remains is actually the truncation error. Okay? That's because for the analytical solution, it's not the numerical derivative that matches, it's actually the analytical derivatives that matches. So the mismatch is actually the truncation error in space and in time. So it's equal to tau, let's write delta t plus tau delta x. So this is what we call the error equation. Okay, in general, the error equation is actually the same as the discretized equation satisfied by the error equation follows a very similar numerical scheme, right? So basically, the error satisfies the discretized version of the differential equation, not the analytical differential equation. It also has a right-hand side. It has an additional term that is equal to the truncation error. I mean, this is actually the error equation is the equation that relates the truncation error, which we can analyze using Taylor series analysis, with the solution error, which is actually the ultimate thing we care about. And that's the reason why in analyzing the solution error, we care about both the truncation error, that is how good our approximation is, and also how stable our numerical scheme is. That's I mean, the reason we care about the stability of the numerical scheme, not the analytical differential equation, is because the error equation is satisfying not the analytical derivative equation, but the numerical derivative equation. Okay. Any questions?